Hi everyone, I'm Jiaoyang and I'm a new assistant professor joining the Robotics Institute. My research is about large-scale multi-robot coordination. With the advance of robotic technologies, there's no doubt that we will see more and more robotic applications in our daily life. Examples vary from smart pod, drone deliveries, automated manufacturing, and autonomous vehicles. When we see so many robots around us, one obvious question is, can we coordinate these robots as a team? Because in this way, the robots may be able to do their own tasks more efficiently, and in many cases, they can do some new joint tasks that a single robot cannot do alone. Therefore, in my research, I'm interested in developing fundamental algorithms to allow a large team of agents to make joint decisions so that they can work on collaborative tasks intelligently in dynamic environments. So for the multi-robot system, we actually look at a variety of them. We look at the general multi-robot motion planning problem, where the robots can be either mobile robots in 2D environments or drones in 3D environments. We also look at more domain-specific applications. For example, in a warehouse, how do we coordinate hundreds of mobile robots to move shelves or inventory pods? And also in a manufacturer, how do we coordinate a team of robotic arms to work on some complex assembly tasks? In addition to robotic applications, we also look at traffic systems. When you have airplanes in an airport or trains on a railway network, how do you coordinate them so that they do not collide with each other, and also they can avoid traffic congestion as much as possible? In addition to physical world, we also look at digital world. Like when you are in a computer game, how do you coordinate a team of game characters so that they can move to their target locations while satisfy some specific constraints required by the game? Among so many different applications, one fundamental question that we need to solve for all of them is the path planning problem. Basically, how we plan paths for these robots or these agents so that they do not collide with each other, and in the meantime, they can reach their destination as fast as possible. So we start with this simplified problem where we have a two-neighbor grid, and we try to plan collision-free paths for this team of agents. We look at a variety of different AI and optimization techniques to develop different algorithms to satisfy these constraints. So we look at optimal algorithms that can solve the problem with hundreds of agents. We also look at suboptimal algorithms that can solve the problem with thousands of agents. So when we have the algorithm ready, then the next question is, how can we move from this simplified world to the real world, where we need to worry about the robotic dynamics for different types of robots, and also all kinds of uncertainties that can happen during the execution of the system, like the uncertainties coming from the inside of the robots, but also some unexpected external disturbance in the system. So our solution to this challenge is basically combining centralized planning with decentralized control. Why? Because our previous centralized algorithm can make really good decisions about the coordination behavior of the robots, but then the decentralized control can give us robustness guarantee so that even if something unexpected happens, the agent themselves can make decisions to react to the changes in the environment of themselves. So we look at the intersection between the centralized planning and decentralized control. For example, when we plan, we want to take into consideration the potential control deviation during planning, or sometimes we want to build an interface between the planning and the control so that the controller can exclude the planners command in real time. And once we have such planning system, the next question is, can we add task planning into the loop? Because usually when we have a team of robots, we want them to navigate, but we want them to navigate to fulfill some joint tasks. Examples like here, we have robots in the warehouse, or we have robotic arms for assembly tasks. And in such combination of tasks and path planning, it's not only about like we do task planning first and path planning later. There's challenges coming from some special tasks that require the joint behavior of multiple agents. Like here, we have this hold and attach operation between multiple robotic arms. And also, in many cases, there's a long task sequence for each robot, and these tasks always have complex dependencies between each other. So how can we combine those tasks and path planning together to handle such complex dependencies? So if you are interested in such multi-robot coordination problems or other types of multi-robot coordination problems, feel free to reach out to me. I'm very happy to discuss with you about such problems. Thank you very much.